So in this video, we're going to be going over balancing redox reactions with three question examples. But before we start, we're going to go over some principles for balancing redox reactions that we need to understand. So in a redox reaction, there are two half reactions take place. And these two half reactions, there's one oxidation reaction where an atom loses electrons. That's an oxidation reaction. And there's also a reduction reaction where an atom gains electrons. So these two half reactions combine to make a redox reaction, reduction and oxidation reaction. In our examples, it's a pair of redox reactions. There's one pair. So this is the principle which you're going to use for our questions. So the first method of which how we're going to balance is oxidation numbers. So this is method number one. So the oxidation number method goes on the following. Electrons are gained or lost from an atom in a chemical reaction. We mentioned there's a pair of oxidation and reduction reactions. You could try to find the oxidation and reduction reaction and use that for the overall balancing. So that's what. But there were some rules for oxidation numbers that must be followed when going over the video. So these rules are very crucial, and that's why we're going to assign an oxidation number for each atom, because every atom in our chemical reaction has an oxidation number. So the rules we could use is that the sum of the oxidation numbers for a neutral compound is zero and there's no exceptions. That means, for example, NaCl, they're going to add up to zero oxidation number. Secondly, oxygen number is negative 2, oxidation number is negative 2, except when we flow as a peroxide. And finally, there's the last rule after the oxidation negative 2 is that hydrogen, the oxygen number is positive 1, and there's an exception when it's a metal hydride. But the exceptions are not going to apply for the first example that we are going. Finally, elaborating on one more thing, elements alone, they also have an oxidation number of 0. These include diatomic elements. So, for example, H2, Cl2, or say Na sodium metal, those all alone would have an oxidation number of 0. So this is our chemical reaction. So we can start by assigning oxidation numbers to all of the atoms involved in this reaction, because we need to figure out which one is the oxidation half reaction, which one is the reduction half reaction in order to proceed with further analysis of balancing. So based on our rules, we know that oxidation is a negative 2 unless it's with a peroxide or it's with a fluorine, none of that exists. Hydrogen is a diatomic element, so we assign 0 automatically. No need to consider any other rules. Hydrogen, as opposed to a metal hydride, it's always positive 1. So we can assign an oxidation number of positive 1, and this can also be applied to NH3 as positive 1. So now oxygen over here can also be negative 2 based on our exact same rules. So NH3, it needs to be neutral compound, it is added to 0. So hydrogen plus 1 times 3 is positive 3. So the nitrogen has to be a negative 3 to balance that all out. Oxygen, negative 2. So the total nitrogen has to be positive 2. So each nitrogen must be positive 1 divided 2 by 2. So having done that, so now we can proceed by identifying the changes in oxidation numbers. So we need to find out which one two other half reactions. We need a pair of half reactions. So nitrogen goes from positive 1 to negative 3. This means it's going down by 4, which is a gain of 4 electrons. So that's the first change. We can identify that half reaction, and this happens for each nitrogen atom. So that must be labeled correspondingly. Now the other one is from the hydrogen in H2 to H2O. Of course, we need to involve separate parts of a reaction. So there is a loss of one electron per hydrogen because 0 to positive 1. So each electron is a negative charge. So since it went up, there's a loss in a hydrogen. So now that we've done this, we can start to identify our coefficients. So we have labeled the subscripts for the N and H. Why do we do this? Because there are coefficients of a cell. So if it's like N2H2, we need to consider that. So we multiply that by 2 because nitrogen is N2 on the left side. Hydrogen both the left and right is times 2. So we put 2. So we multiply both sides by 2. We end up with 2 electrons and 8 electrons. Our next step is to find the lowest common multiple for these numbers. So the lowest common multiple for 2 and 8 is going to be 8. 2 is a factor of 8, so we just multiply 2 by 4, we end up with 8 electrons, and having done this, we can get into balancing. And just to further explain the least common multiple, here's a brief idea. So, in these reactions, the number of electrons has to remain the same. It's because the charge has to remain the same, and matter is neither created or destroyed. We are not losing any matter outside of the reaction. So, if the electron changes are not the same, if the same number of electrons are not lost and the same number of electrons not gained, we're going to end up with a different number of total electrons, which violates this principle. So that is why we have to figure out the least common multiple in order to ensure that the change, the gain, is equal to the loss of electrons. In our oxidation numbers, we can now go on to balancing since we know which one is our oxidation, which one's a reduction. If we identify that, it means we showed it. So we're going to apply the multipliers as coefficients to this. So starting off with this one, times 2 is happening because of the subscript for this nitrogen, but since the only subscript is there, we do not need to change this number. We don't need to add a coefficient over here for the dinitrogen monoxide. But over here, there isn't one, so we need to put on a 2. Now, hydrogen is being multiplied by 2 and 4. So this 2 multiplier does not need to apply to any of them because they both already have H2 together. But the multiply by 4, the coefficient of 4, we have to add. But we can just add it to both sides because on the right side, hydrogen is in form of H2O and NH3, so it won't be balanced. So rather we're going to have to rely on balancing by inspection, so we can only balance one side. So as per a typical case, we are going to go by balancing the left side just. So now that we've done that, let's check to see by inspection how the rest of the numbers add up. So nitrogen, there's 2 nitrogens here, there's 2 nitrogens here. That seems correct. Oxygen, there's 1 oxygen here and 1 oxygen here. That seems correct. Now for hydrogen, there's a total of 8 hydrogens on the left side. On the right, there's 6 plus 2 equal to 8 hydrogens. So all the atoms are balanced. By inspection, we have managed to check that. So this is our final answer for the balancing by oxidation numbers method.
Looking at question 18 in the balancing with acids sheet, we can see that we have Zn plus NO3 minus produces Zn2 plus NH4 plus. For this question, we are going to be balancing using the ion electron method in an acid, so let's get straight into it. In an acid, we have H2O and H plus ions. We'll be using these to determine what to add in order to balance this reaction. Before we get to balancing, let's quickly make a table summarizing what to add if we want to balance each half reaction. On the left, it's what we want, and on the right, it's what we'll add. What we're adding is based on what can be found inside an acid, which includes H2O and H+. In green, let's write oxygen, and if we want oxygen, we'll add H2O to the equation. In blue, we'll write hydrogen, and if we want hydrogen, then we'll be adding an H+ to the equation. Lastly, if we want to add electrons, we'll be adding them to the more positive side of the half reaction. Now let's write our two half reactions. We're going to have reaction A and reaction B for the big reaction up above. Using my yellow highlighter, I'm going to highlight the reactant and product for half reaction A, which is Zn and Zn2+. Now using my pink highlighter, I'm going to highlight the reactant and product for half reaction B, which is NO3 and NH4+. These highlights are going to show where the reactants and products are going to be and in which half reactions they're going to go in. For half reaction A, we're adding Zn with an arrow and a little bit of space, and then Zn2+. For half reaction B, we're writing NO3 arrow, leave a bit of space, and then NH4 on the other side. Before doing anything, we first need to make sure that both sides are balanced by inspection. We can see that there's one Zn on each side, so it's already balanced, and one N on each side, already balanced. So now we can keep going and start balancing using OH and electrons. Starting with oxygens, we can see that reaction A doesn't actually have any oxygens, so we can go straight to reaction B and add oxygens there. In reaction B, there's 3 oxygens on the left side and 0 oxygens on the right side. So according to our table, in order to balance this, we'll need to add 3 H2Os to the right side. And we did that in green just to match our table. Again, looking at reaction A, there's no hydrogens, so we don't need to balance anything there for now, so we'll go straight to reaction B. In reaction B, there's a total of 10 hydrogens on the right side and 0 hydrogens on the left side. On the right side, there's 6 from H2O and 4 from NH4+. According to our table, we'll add 10H plus to the left side, and we're doing that in blue to match. Now let's find the overall charge on the left side and right side for reaction A in order to determine how many electrons we need to add and where we should add those electrons. There's an overall charge of 0 on the left side and an overall charge of 2 plus on the right side. Let's highlight that in orange. We can see that the overall charge on the right side is more positive, so we're adding electrons to the right side in red. We want to make the overall charge on the left side and right side the same, so we're adding 2 electrons to the right side in order to make the overall charge for both sides 0. Now let's do the exact same thing but for reaction B. The left side has an overall charge of 9 plus, while the right side has an overall charge of 1 plus, and let's highlight those in orange as well. Since the left side is more positive, we're going to be adding electrons to the left side in red. And in order for both sides to be the same charge, we're adding 8 electrons, which will make both sides have an overall charge of 1 plus. Before we go on to the next stage of balancing, we're going to find the LCM of the electrons in both half reactions. The LCM between 2 and 8 is 8, so we're going to be multiplying reaction A by 4, which means all the coefficients are going to be multiplied by 4 in order to make the number of electrons 8 electrons for both half reactions. Coefficient for Zn changed to 4, the coefficient for Zn2 plus changed to 4, and the number of electrons changed to 8 electrons for reaction A. Since the LCM was 8, we never really changed reaction B, so we're just going to copy and paste everything from reaction B as the same in the second stage. Now we're going to identify common species in both half reactions. As we can see, 8 electrons is common in both half reactions, and that's the only one, as H plus and H2O do not occur in both reactions. The final step is to write the complete full form of our final balanced reaction. Everything that wasn't cancelled out in the previous stage is now going to be in our final answer, which means the full reaction is 4Zn plus NO3 minus plus 10H plus produces 4Zn2 plus NH4 plus 3H2O. Just to check that our final answer is right, we can see that the coefficients of Zn and Zn on each side are the same, N is the same on each side, H is the same on each side, and O is the same on each side. We can also see that the overall charge on both sides is 9 plus, which means that it is completely balanced using the ion-electron method in an acid. Looking at question 28 in the balancing with bases sheet, we can see that we have Cl2 produces ClO3 minus plus Cl minus. For this question, we're going to be balancing using the ion-electron method in a base. In a base, you have water and hydroxide ions floating around, so we're going to be making a table that incorporates these in order to balance using a base. In green, let's write oxygen, and if we want to add oxygen, then we'll add 2 OH minus to the side that needs oxygen and H2O to the other side. Let's write hydrogen in blue. If we want to add hydrogen, then we'll add H2O to the side that needs hydrogen and OH minus to the other side. Let's write electrons in red, and if we want to add electrons, then we'll be adding it to the more positive side. Now let's write our two half reactions, one being reaction A and one being reaction B. Using our yellow highlighter, we're going to first identify reaction A, which will be Cl2 and ClO3 minus. As you can see in the original reaction, there's only one reactant, which is Cl2, which means we'll be using Cl2 again in reaction B, as well as Cl-, which will indicate using our pink highlighter. Now let's write half reaction A, which is Cl2 on the left side, leave some space, arrow, and ClO3 minus on the right side. Now let's write reaction B, which is Cl2 on the left side, some space, an arrow, and Cl minus on the right side. We now have to balance by inspection, and we can see that there's two Cl's on the left side, whereas there's only one Cl on the right side for both half reactions. To fix this, we can just add a 2 coefficient in front of both ClO3 and Cl minus. In reaction A, we can see that the right side has 6 oxygens, while the left side has 0 oxygens. To balance this, according to our table, we have to add 12 OH minus to the left side and 6 H2O on the right side in green. And now we can see that there's 12 oxygens on the left side and 12 oxygens on the right side, as well as 12 hydrogens on the left side and 12 hydrogens on the right side. So the reaction A is balanced. Let's look at reaction B. We can see that there's no oxygens or hydrogens on either side, so we can go straight to balancing the number of electrons. Let's identify the overall charge on the left side and right side of reaction A, 12 minus on the left side and 2 minus on the right side. After highlighting that in orange, we can see that the right side is more positive, so we'll be adding electrons to the right side. To make both sides have the same overall charge of 12 minus, we're going to be adding 10 electrons to the right side. Doing the same thing for reaction B, the left side has an overall charge of 0, while the right side has an overall charge of 2 minus, and we're going to highlight that in orange as well. Since our left side is more positive, we're going to be adding our electrons to the left side. We're adding 2 electrons because we want to make the overall charge for reaction B on both sides be the same, which is 2 minus. Now we have to find the LCM of the number of electrons, which is between 2 and 10, and the LCM between them is 10. So we're multiplying reaction B by 5, and each coefficient will be multiplied by 5. Now let's write the updated half reactions below. Reaction A hasn't changed, so it's just copy and pasting the exact same reaction below. Reaction B, however, is being multiplied by 5, so each coefficient will also be multiplied by 5. This means that we'll write 5Cl2 plus 10 electrons produces 10 Cl minus. Now we have to cancel any common species that appear between reaction A and reaction B. We can see that it's 10 electrons and 10 electrons which cancel each other out. However, there's nothing else that we can cancel which are common. Thus, we can write the final full reaction at the bottom. Since there's Cl2 and 5Cl2 and they're both common, we actually add them together instead of canceling them out. So in our full reaction, we'll write 6Cl2 plus 12 OH minus produces 2ClO3 minus plus 6H2O plus 10Cl minus. We now have our full balanced reaction. We can see that there's 12 Cl on the left side and right side, 12 oxygens on the left side and right side, and 12 hydrogens on the left side and right side. So all the coefficients add up. We can also see that the overall charge on the left and right side is 12 minus, meaning that this answer is completely balanced.